Let us begin this week with a calculus exercise. Let's say you want to evaluate the integral from 0 to 1 of x squared dx. How are you going to do this? Well, you might say, that is easy. I know that the integral of x squared is equal to 1/3 times x to the power of 3. So evaluating it at 1 and 0 gives me the result of 1/3. So here you are taking an analytic approach where you try to directly find the integral using calculus and calculate its exact result. Or you might try to find this numerically. Recall that the integral from a to b of fx dx gives you the area under the fx curve between a and b. For our example, fx is equal to x squared, and we're interested in the interval between 0 and 1. So in this plot, this area under the black curve between 0 and 1 is equal to the integral we want to find. You can see from my plot over here that we can try to approximate this with a bunch of rectangles. We can divide the interval between 0 and 1 into k equally spaced intervals, each with sides d. Then the kth rectangle will have base of d and height equal to the function x squared, evaluated at the midpoint of this rectangle. So for the kth rectangle, the height is given by kd minus 1/2 of d squared. Then we can see that the area under this curve is approximately equal to the sum of the areas for all of these rectangles. In other words, the integral from 0 to 1 of x squared dx is approximately equal to the sum over all k's of the base d times the height kd minus 1/2 of d squared. And as your d, which is your bandwidth, gets smaller and smaller, this approximation is going to get more and more accurate. This method is known as numerical quadrature. However, the focus of this week, our lectures, is another class of methods for approximating this integral, and that is called the Monte Carlo integration. Since we're already talking about the area under the curve, let's notice that the area under x squared between 0 and 1 is a portion of the area of the unit square, where both x and y range between 0 and 1, and the unit square has area of 1. Here's a plot that shows this. This is the unit square, and we're interested in finding the integral, which is the area under this curve. So intuitively, we can randomly sample 10,000 or even more points from the unit square. And for each of the random points that we draw, we try to find whether this point is under this curve within this area we're interested in, or is it outside this area. If it's within this area, we denote the point by orange, otherwise we denote it by gray. Then intuitively, the area under the curve is approximately equal to the proportion of orange points in our 10,000 samples times the area of the unit squared. You can also notice that this method is random in its nature. Because every time we randomly draw 10,000 points, the points every time that are drawn are going to be random, and the resulting proportion of orange points is going to fluctuate as well. Monte Carlo methods are a class of computational algorithms that rely on repeated random sampling to obtain the results. This week, we will introduce Monte Carlo integration, which are a set of Monte Carlo methods for evaluating integrals. We will start from introducing simple Monte Carlo estimators for bounded and unbounded integrals, and then we will move on to discuss how we can approximate the standard error of these Monte Carlo estimators. Note that the Monte Carlo approach to estimating the integrals is random in its nature. So it has random standard errors associated with them. But before that, let's talk a little bit about the history trivia behind these methods and where does the name Monte Carlo come from. The systematic development of Monte Carlo methods started in the 1940s at the Los Alamos National Lab. The Los Alamos National Lab was founded during the Second World War, and they invited a lot of physicists to participate in the Manhattan Project, which involved the development of nuclear weapons. During the 1940s, the first digital computer, ENIAC, was being built at the University of Pennsylvania. And you know that during that time, computers were still not for personal use, they were for military uses. So von Neumann, who is the father of modern computers and also a consultant to Los Alamos at that time, asked the scientists at Los Alamos, particularly Frankel and Metropolis, whether they would be interested in developing some tests for the ENIAC to test its computational capacity. So Frankel and Metropolis started to develop those tests. I guess mainly a lot of physics-related computations for ENIAC. And then when they carry out those tests, they have meetings within the Los Alamos with von Neumann, and then they report the results of the evaluations to the audience. And when they were having this kind of meetings, in the audience was Ulam. Ulam was another scientist who was working at Los Alamos during that time. He just returned to Los Alamos during that time after a brain inflammation. So he earlier had a brain inflammation where he had to undergo a surgery. And while he was recovering from the surgery, he was playing a lot of solitaire. And the story is that when he played a lot of solitaire, he kept losing and he became interested in approximating or calculating what is the chance of me actually winning the game if everything is random. And you probably learned in your, or did this kind of exercise in your beginning statistics or probability course, where they ask you if you draw two cards, what is the chance that you get a 4 and a 7, etc. So you can use permutations and combinations to calculate this. However, to exactly calculate the chance of winning a game, you can see there are so many possible combinations of events, and the computation is going to get extremely tedious. So he thought, maybe I can play the game hundreds of times and then use this to estimate the chance of a successful outcome. So, as I said earlier, he was in the audience when they were trying to develop the tests for ENIAC, and he realized that the availability of computers made this kind of statistical methods where I can randomly simulate the games or some kind of events and try to estimate something very practical. And this sparked the development of a class of statistical approach to computationally tedious tasks. When von Neumann asked them to come up with a name for these approaches, Metropolis suggested Monte Carlo. This was partly due to the fact that Ulam often mentioned his uncle who would borrow money from all the relatives because he just had to go to the Monte Carlo casino in Monaco. At the same time, the name Monte Carlo, which is related to the casino, perfectly captures the spirit of randomness for this kinds of procedures.